All right, moving on to question 4. In scenario 1, a swimmer holds a block, mass M at rest. We got mass M at rest in a tank of fresh water with a density rho 1. The block is released from rest and accelerates upward with an initial acceleration a1. All right, so basically what's happening here is, of course, this is a buoyant force type problem. We have an FB going upwards. I drew my vector slightly larger, and then we have an FG going down, and that's going to be accelerating upwards because our FB is greater than our FG. Now it says that in scenario 2, the swimmer holds the same block at rest in a tank of salt water with density rho 2, where rho 2 is greater than rho 1. The swimmer again releases the block from rest, and the block accelerates upward with an initial acceleration a2. All frictional forces are negligible. All right, so if you look at A is over here. It says indicate whether A1 is greater than, less than, or equal to A2 by running one of the following in your answer booklet. So I have A2 is greater than A1. Justify your answers in terms of all forces exerted on the block. And it says use qualitative reasoning beyond referencing equations. All right, so again, my answer is a little bit abbreviated, but we have the net force, which is M times A, equal to the buoyant force upwards minus the FG downwards. So MA equals rho VG minus FG. And I said if rho 2 is greater than rho 1, then my buoyant force 2 must be greater than my buoyant force 1 because rho VG is the product of three numbers that obviously includes rho that gives us our FB. So FB2 must be greater than FB1. And then if you have more buoyant force, then you have more net force, and that equals more upward acceleration. So I would have written some of those things down along with a few sentences to back up some of my work. Now for B, it says, consider the general case where a block of mass M and volume V is completely submerged in a fluid of density rho, starting with Newton's second law, derive an expression for the initial upward acceleration A of the block when the block is released from rest. Express your answer in terms of M, V, and rho and physical constants. As appropriate, begin your derivation by writing a fundamental physics principle or an equation from the reference information. All right, so I start off with Newton's second law right over here. Okay, again, I knew that the sum of the forces was my buoyant force minus my Fg, so then I expanded those out into rho Vg minus mg. The g got pulled out in front, got factored out, and then I have rho v minus m. Okay, the rho is circled over here to prove a point for part C, which I'll get to in a moment. And then because of the initial m there, there's an m in the denominator. So A equals G, parentheses, rho V minus m over m. For part C, indicate whether the expression for the acceleration you derived in part B is or is not consistent with the claim made in part A. Briefly justify your answer by referencing your derivation in part B. So that's where I'm talking about this part over here. So it is consistent. If the rho is bigger, then the FB is bigger, then the acceleration is larger. And you could talk about how this rho over here would make the numerator greater overall. And if the numerator was greater, then mathematically your overall number and acceleration is going to be greater. So again, I would point to certain parts of that formula, and then with my justification, I would add a few sentences.